Good day, everyone. I'm going to present for Group 5. We were looking at market basket analysis, which is also known as association rule mining. So we're going to first look at what this concept is and also look at a little bit of some terminology to just get us going and help us understand the whole concept behind market basket analysis. So market basket analysis is a very popular technique within the retail industry. It is used to uncover associations between items by looking for combinations of those items within transactions, how often they occur, and also whether it is by coincidence or not. So there will be a couple of different measures that we'll also look at. So basically, this allows retailers to identify relationships between items that customers buy. This technique, though famous in the retail industry, can be applied to any field or profession. It can be used by anyone or any organization that seeks to improve its decision making. Examples could be medical diagnosis, geographic information systems. It could be applied to relational databases, large database, or distributed databases, etc. So some of the terminology that we need to understand is listed on this slide. We have a transaction, which is a complete record made up of underlying items. For example, a customer's purchase in a single visit. Then we have an item set. This is a subset of items within a transaction. So it could be one item, it could be two items, or it could be the entire transaction. For example, here in a transaction with milk, bread, eggs, and coke, just eggs and coke, the two of them could be a subset of that transaction, could be an item set of that transaction. Then the following two terms are quite key, where the antecedent, which is the left-hand side of a rule. Rules have a left-hand side and the right-hand side. So the left-hand side is what is called the antecedent. In a rule with milk, bread versus eggs and coke, milk and bread becomes the antecedent. Then we also have the consequent, which is the opposite of the antecedent. It is on the right hand side, and going back to our example, eggs and coke become the consequent. The following slides will look at, so the next 3 slides are going to look at some key measurements in market basket analysis, which are support, confidence, and lift. These 3 measurements together will help us do the association rule mining. So support refers to the default popularity of an item and can be calculated by finding the number of transactions containing a particular item divided by total number of transactions. Support for item B can therefore be calculated mathematically as support B is equal to transactions containing B over total transactions. For instance, if out of 1,000 transactions, 100 transactions contain pasta, then the support for pasta is 100 over 1,000, which is 10%. So basically, it's the frequency of getting pasta in a set of transactions. So here we have 10% of the transactions containing pasta. Then we go into confidence. Confidence refers to the likelihood that an item B is also bought if item A is bought. So this means confidence is the likelihood that the consequent is selected if the antecedent has been selected already. It can be calculated by finding the number of transactions where A and B are bought together divided by the total number of transactions where A is bought. So mathematically, this is represented as confidence AB is equal to transactions containing both A and B over transactions containing A. Going back to our pasta example, if 50 transactions contain pasta and escalope, that is A and B, and 150 transactions contain pasta, we have 50 over 150, which comes down to 33.3%. So that is the confidence we have that when pasta is bought, escalopes are also bought. Then the third and probably the most important out of the three is lift. Lift A and B refers to the increase in the ratio of sale of B when A is sold. So it basically tells us that the likelihood of buying pasta and escalope together is 3.33 times more likely than the likelihood of just buying the escalopes alone. A lift of 1 means there is no association between the products A and B, pasta and escalope. Then a lift of greater than 1 means products A and B are more likely to be bought together. Then finally, a lift less than 1 refers to no likelihood of the two products being bought together. So the reason I say this is probably one of the most important measures, we could have very high confidence or very high support, but if we end up getting a value 1 or a value less than 1, then we have no confidence that the two items will be bought together. So lift along with the other three gives the final decision of how strong the association is. So we'll now get to implementing this concept in Python. So I'll switch over to my live Jupyter notebook for explanation of the code. So allow me to switch over to the live Jupyter notebook, but you'll also be able to get the explanation within this presentation, which we are going to share. So just a moment as I switch over. I hope this is visible. So the first thing we need to do is to import all our necessary libraries. I'm going to run this cell here. So please note the a priori algorithm, which contains the a priori class that we need, is not pre-installed in the Jupyter environment. So you will need to install it before you can use it, which is what this next line here does. You can run an exclamation mark, then pip install a priori, and it will install it for you. Then you can then proceed. So the exclamation mark is just to tell Jupyter that you're running this as if it's a terminal command, as if you're running it in the command prompt. So I'm not going to run it because I've already installed. Then this line, our data, reading our data from the CSV file, and header is equal to none because our CSV had no header line. I'll run it. Then just a quick check of the data set. There's our data set. It has been given a generic headers because it had no pre-specified headers. It was just the data itself. So moving on, we can do a DF shape. We see that we have 7,501 rows representing 7,501 transactions. Then we also have 20 columns, each column representing an item, a product. Then we get to this part where we have these few lines of code. The a priori class that we are dealing with does the heavy lifting for us of looking for associations within the data and how strong they are, but it requires us to pass it an iterable object in the form of a list of lists. So this is what this code here does. We start off with an empty list code records, then we have two loops. So the list of lists is in the form of an outer loop and several inner loops. An outer list and several inner lists. Each outer list, the outer list represents the data set, and each inner list represents a transaction. So this is what the four loops are doing. The first one represents the outer list. Then the second one within this block of list comprehension is going to generate the inner list. We have also gone on to remove non-values, because when we ran it first we got 18 associations, but when we removed the non-values, the number of associations dropped to 9. So probably those non-values contributed to some sort of patterns, but since they don't mean anything, we just decided to remove them. So I'll run this line of code. It is finished, and then it gives us 7,501 records, which is the same as our original data set, which had 7,501 transactions. Then we just take a look inside the records list that we just generated. This is what we get. So you can see we have shrimp, almonds, avocado, vegetables, mix grapes, etc., etc. This is what we get. This is the form that the a priori class expects. So let me just add a line here to show you that this is actually two lists, a list of lists. I will run records. So you can see by these two square braces that the outer one represents the outer list, and then the first transaction is from this second square brace up to this point here, up to this brace. Then that's one transaction. Then we have another transaction. Then if we go to the end, we also have the last square brace closing off the outer list. So moving on, we get to the heavy lifting part where the a priori class does the complicated stuff for us. So here we are saving the results of the a priori calculations, the results of its computations into the variable association rules. So it expects the iterable object that we created, which is the records. Then, so it's interesting what happens here. The a priori class tries to uncover all of the possible associations within the data, and this is so demanding. So many combinations. You can imagine the number of combinations from 20 products. So to try and minimize all that computation and just get what we need, we give it some minimum thresholds. So this is minimum support, mean support, and then mean confidence, mean lift, and then mean length. The mean length refers to the minimum number of items in each row that we expect. So in here we are specifying two, just two. These figures are just arbitrary. We can just play around with them, but they are very essential in minimizing the computation time or computational load that we get from this a priori class. So I'll run that as well. So it is finished, and then association results, we are passing it to the list function to represent it as a list. Then we're going to print the association results. So we get 9 rows from these specifications, these minimum thresholds. They give us 9 associations. If we change any of these values, this number might change or might not change. Then we print only the first association. So this format is a bit cluttered and it's difficult to read. This is solved with this section of the code which tries to print it out in a more readable form. And I'll run that, and it gives us the 9 associations that we computed above. So the explanation for these results, here we see the association mushroom cream sauce and escalope. It is a support of 0.005. That means the number of times mushroom cream sauce and escalope were bought together. Then we go on to the confidence, which is 0.3 or 30%, meaning the likelihood that escallops are also bought when mushroom cream sauce is bought. And finally, a lift of 4.7. Sorry, for mushroom cream sauce and escallop is supposed to be 3.7 actually. So a lift of 3.7, meaning the likelihood of buying mushroom cream sauce and escallops together is 3.7 times more than the likelihood of just buying escallops alone. So this is basically what market basket analysis is all about. It's all about uncovering those underlying associations um, between products purchased together, or patterns of data elements that occur together. Thank you.